Okay, the first significant digit in any number must be 1, 2, 3, 4, 5, 6, 7, 8, or 9. It was discovered that first digits do not occur with equal frequency. Probabilities of occurrence of the first digit in a number are shown in the accompanying table. So let's look at this real quick. So a 1 occurs about 30% of the time, a 2 about almost 18%, a 3 about 13%. If you keep on going down, a 9 occurred a little less than 5%. So a 9 is, less than more than 6 times is likely to occur as a 1. So a 1 is 6 times more likely to occur than a 9 is another way to put it. Same thing for an 8. So let's look at this. The probability distribution is known as Benford's law. For example, the following distribution represents the first digits in 184 allegedly fraudulent checks written to a bogus company by an employee attempting to embezzle funds from his employer. Completes parts A through C below. Okay, because these data are meant to prove that someone is guilty of fraud, what would an appropriate level of significance be when performing a goodness of fit test? So we want to be really sure. We don't want to accuse somebody if they in fact did not do it. So we're going to select the lowest possible one they have here, 0.01. Okay, using the level of significance chosen in Part A, test whether the first digits in the allegedly fraudulent checks obey Benford's law. Do the first digits obey Benford's law? What are the null and alternative hypotheses? So remember, the null is always the dull. They obey. The alternative is that they don't obey. Okay, now let's run the test. So I'm going to pull this in to StatCrunch. Okay, so we're going to run our test, and it says perform a goodness of fit test. So you're going to go to stat, goodness of fit, chi-squared. So our observed columns, let me look at these again, are the frequencies. So this is what we observed. It's expected that we get this probability distribution here, right? That's what Benford had deduced, had computed. So run on out. So like it was observed that 36, let me pull up both of these. So ordinarily you'd be computing this expected by hand, but StatCrunch does that for you. So we observed 36. So out of 184 though, the expected amount would be 55 or so, right? So 30% of the 184. And then about 17.6% of the 184 should be the next digit. But looks like it's different. I mean, this first one appears to be more, right? I mean, less. So the observed 36, it should have been closer to 55, and so on. And what's our chi-square statistic? 22.7. That's pretty high, right? Oh, wait a second. I got to get it to 3 places. Hold on. So 22.707. What's our p-value? 0.004, right? 0.004. That's a pretty low p-value, right? I mean, it's definitely lower than 0.01. So we're going to reject HO, right? So we're comparing our p-value, 0.004, to our alpha. P-value is lower than alpha. We reject HO. Because the calculated p-value is less than the given alpha level. So based on the results of Part B, could one think the employee is guilty of embezzlement? Yes. I mean, the first digits do not obey Benford's law. So I hope that helps.